Hello friends. In the previous class we have started with the module number 4, the field effect transistor, and we have discussed about basic PN junction operation. In today's class we will discuss the small signal equivalent circuit. So in order to analyze a transistor circuit, we need a mathematical model or any equivalent circuit of that particular transistor. So the usual or the most popular method or model is a small signal equivalent circuit. Here in this small signal equivalent circuit, it is applied to transistors that are used in linear amplifier circuits. So this equivalent circuit is going to introduce frequency effects in the transistor through the equivalent capacitor resistor circuit. Therefore, the various physical factors in the junction field effect transistor that are affecting the frequency limitations will be considered, and a transistor cutoff frequency, which is a figure of merit, is also going to be defined in the later. So first we'll discuss the small signal equivalent circuit. So here the figure shows the cross section of JFET source and drain series resistance. So the cross section of a N channel PNJFET, that is junction field effect transistor, is shown here in the figure. It consists of the source and drain series resistance, that is RS is the source resistance and the RD is the drain, so which are series resistances. So source and drain series resistance are shown here in the figure, that is RS and RD. The substrate may be a semi-insulating gallium arsenide. The substrate that is marked in the figure is nothing but it is a semi-insulating gallium arsenide, or it may be a P plus type substrate also. So this figure shows the cross sectional view of a JFET. So this figure B that shows small signal equivalent circuit of JFET. So small signal equivalent circuit need to be drawn here first. There are various terms like CGD, VGS, VG bar, VG dash, S dash, RGS, CGS, GM, VG dash, S dash, RDS, CDS, RD, CS, RS. All these parameters are used here. So we'll see what are those parameters. The voltage VG dash, S dash, the first input at the input side, that is at the gate, it is the internal gate to source voltage. So GS stands for gate to source. So it is the internal gate to source voltage that controls the drain current. Next comes the RGS and CGS. So the RGS and CGS, these are the parameters which are going to the gate to source diffusion resistance. Gate to source diffusion resistance, that is RGS, and junction capacitance. So RGS is nothing but a source to drain, gate to source diffusion resistance, and CGS is junction capacitance. Then the gate to source junction is reverse bias for depletion mode devices and has only a small forward bias voltage for enhancement mode devices. we know that the JFET has two types, that is one depletion mode and the enhancement mode. So gate to source junction is reverse biased for depletion mode device, whereas it has only a small forward bias voltage for enhancement mode JFET. So that normally RGS, that is gate to source diffusion resistance, is large here. So the parameters RGD and CGD, the next comes the RGD and CGD are the gate to drain. GD stands for gate to drain. So these are the gate to drain resistance and capacitance respectively. So RGD is a gate to drain resistance, whereas CGD is a gate to drain capacitance. The resistance RDS. So RDS is the finite drain resistance. RDS is a finite drain resistance, which is a function of the channel length modulation effect. Then the CDS. The CDS capacitance is mainly a drain to source parasitic capacitance. And the last one is CS. CS is the drain to substrate capacitance. So these are the parameters that are used here. Then the GM-VGS. GM-VGS is a transconductance. GM-VG dash S dash. So this third figure shows the ideal low frequency small signal equivalent circuit. So the ideal small signal equivalent circuit is shown in figure C. So all diffusion resistances, so whatever the diffusion resistances that are shown are infinite and the series resistance are 0. So this is the method to redraw the circuit. So all the diffusion resistances are infinite and the series resistance are 0, and at low frequency the capacitance becomes the open circuit. So if you want to draw a AC equivalent circuit for any network, you need to set the DC sources to 0 and replacing them by a short circuit equivalent, then replacing all the capacitors by a open circuit. So removing all the all elements bypassed by the short circuit equivalent that are introduced previously, then redraw the network. So here the diffusion resistances are infinite and the series resistance are 0, and the low frequency capacitance becomes open circuit. So the small signal drain current is given by IDS equal to GM-VGS. So the small signal drain current is given by IDS equal to GM-VGS. So which is a function only of the transconductance and the input signal voltage. GM is the transconductance and VGS is the input signal voltage. So the IDS, the drain to source current, IDS, is nothing but it is a function of the transconductance and the input signal voltage, GM VGS. That is equation number 1. Now see the figure B. It shows the ideal equivalent circuit including the resistance RS. So the effect of the source series resistance can be determined by using this figure D. So we have IDS equal to GM into Vg dash S dash. So that is equation number 2. So the relation between VGS and Vg dash S dash can be found from VGS equal to Vg dash S dash plus Gm into Vg dash S dash into Rs. So that is equal to, just take Vg dash S dash common, 1 plus Gm Rs into Vg dash S dash. So we can write the equation number 2 as IDS equal to Gm into Vg dash S dash. So replace the value of Vg dash S dash. So we will get IDS equal to Gm divided by 1 plus Gm into Rs into whole bracket VGS. So that is nothing but Gm dash into VGS. So the effect of the source resistance is to reduce the effective transconductance or transistor gain. So here Gm is a function of the DC gate to source voltage. So Gm dash will also be a function of VGS. Thank you for watching the video.